We are on the day 18 of this challenge, where we are doing 30 deep learning projects in 30 days. So the day 18 problem looks like that we are going to go a little deeper in the LSTM model, where we add attention mechanism to LSTM model for machine translation. So this is split into 2 days. Today we will go into the theory only, and tomorrow we will explore the coding part. So yes, let's start. Let's start. I will go and close this window, close this thing, and do what? Use Chat GPT's same window to help me out. So I'll say, hey, it is day 18, and here is the problem statement for today's. Uh, so let's start. What it says. Uh, okay, it is opening. There is a bug, I think. So it keeps on opening the old thing. It's the old response, I guess. So yeah. So on the day 18, it says that let me do what? Oh, I cannot change the. So this is the minimum. Uh, okay, I can do that, but I cannot minimize that. Okay, this section. Okay, so it says welcome to day 18 of our deep learning challenge. Today we will explore the theory behind the attention mechanism and understand how it can be added to an LSTM model for machine learn translation. We will focus on building a foundation that will help us implement this mechanism in the code tomorrow, which is day 19. Correct. That's what we want. So what is attention? Um, in machine learning, like translating text from English to French, in an LSTM processes the entire input sentence and then tries to generate the translation. Okay, the problem is that as the sequence gets longer, the LSTM starts to forget the part of the information it has received in the start earlier. This makes it difficult for the LSTM to properly handle long sentences because it loses important details. Okay, the attention mechanism helps solve this problem by allowing the model to focus on relevant parts um, of the input sentences at every step of the output generation. So it says the attention mechanism solves helps solve this problem where the LSTM forgets, in case of the long translation, the long sentence, forgets the initial parts. So it solves this problem by allowing the model to focus on relevant parts of the input sentence at every step of the output generation. Okay, we did see this thing, as in we did learn about LSTM yesterday, where we saw it has two important things, uh, gates and memory memory cell. Okay, if I go back, and if I go back here, here if I want to see, yeah, it has a called cell state and then gates. Because of with the help of these two, it remembers the important information at each step, right? So we did learn about that. So LSTM solves the problem by remembering or focusing on the relevant parts of the input sentence at every step of the output generation. Essentially, it is like the model asking itself which words in the input sentence are most important for generating the next word, and then focusing on those parts, in specific parts. So it focuses on, like in the translation example, it focuses on uh, what important parts of the are focuses on the input sentences that are important parts for generating the output sentences word. And how does it know which parts are important? That we are going to learn later. If this will not explain nicely, I'll go and ask. So what is this attention mechanism? So the attention mechanism is a method that allows the model to selectively focus on different parts of the input sequences. It is a method that allows the model to selectively focus on different parts of the input sequences. Okay. Hmm. Instead of relying solely on final input of an LSTM, which might be missing some important details, the attention mechanism assigns weight to each input word to decide how much attention should be paid to each word and then producing the next word on the output. Okay, so this attention mechanism is the method that allows the model to selectively focus on different parts of the input sequences. Instead of relying solely on the final output of the LSTM, the attention mechanism assigns weights to each input word to decide how much attention should be paid to each word when producing the next. Okay, so it assigns weights to each input, and on the basis of those weights, uh, it decides how much attention should be paid to each word for generating the next word and the output. Think of it like reading a book and summarizing it. Instead of trying to remember the entire book, you selectively look back at the important sections that are more relevant to the summary you are writing at that point moment. Correct. So what I usually do, I underline or use a highlighter to mark the important lines of the from the chapter of the book. So it helps me to go back and revise or remember the important points only, and not to remember everything from the chapter. This is exactly what it is doing. Maybe uh, it assigns important weights to the each input, and based on those weights it decides how much attention it should give to each word for predicting the next output word. So how does this attention work in LSTM? Attention work in three main steps. First is scoring. Calculate a score for each input word to determine how important it is for current output word. Okay, it calculates a score for each input word to determine how important it is for current output word. Okay, so it calculates score for the current output word. We do not know about the next word, but we do know about the current output word. So based on that, it assigns calculate a score for each input word. Now, weighting. Use these scores to generate weights. Not weighting, this is weighing, which determine how much attention each word should receive. So, it uses the scores that we had calculated from step number one to generate the weights. To generate the weights. And in the next step, which is context vector, use the weights to create a context vector, which is a weighted combination of all input words. This context vector is then used along with the LSTM's hidden state to predict. Okay, so it creates a context vector which is a weight combination of all the input words. This I'll see what it is. I don't understand how does it decides or come to this combination of the input words, but it does have a combination of the weights of all the input words. So and it is called as context vector, and this weight is then used within the LSTM hidden state to predict the next word. Okay, so let's break down these steps in a similar way. So if we break down the steps, the model in the first step, which is scoring the input words, which is to calculate the score for each input word. is that the model computes a score for each word in the input sentence to determine its relevance for generating the current output word. Okay. This score is usually computed based on the current hidden state of the LSTM and each of the input word. Think of this as the model deciding which part of the input are important based on the current output that it is generating. The score can be computed using a simple neural network layer that takes the LSTM hidden state and each input word as input and produces the score. Okay, so it uses the current word, output word, and based on that, it generates the score for each input word. I'll still rely on some good example, but let's move forward to step number two. The scores are then normalized using a technique called softmax. Okay, softmax we have learned the activation function, which converts the outputs the value of neurons in the form of probability, and the sum of such that the sum of the output of all those neurons is one. So this it uses softmax to normalize the score. So softmax converts these scores into values between 0 and 1 such that all the values add up to 1. Same thing that I've just talked about. And then these values are called attention weights. These values are then called attention weights. The higher the weight, the more attention that word will receive. Okay. So from the score, the so basically the scores have been generalized using softmax so that they lie between 0 to 1. Nothing much has been done here. And it says that the higher the weight is, the more attention the word will receive. Okay. Softmax function makes sure that the weights are easy to interpret as probabilities, which help the model decide how much each word contributes to generating the current. Okay. Yes, with the why we are using softmax, it says that with the help of softmax, it is easier to interpret as probabilities, the weights. Again, same thing that I've talked about. So the second step is all about normalizing the scores that we have calculated in the step one in the form of probabilities, as in they should lie in between 0 to 1 such that the sum of all the values add up to 1, and they are called attention weights. Then in the in the third step we do what? The model then uses these attention weights to compute a weighted sum of all the input words, and this weighted sum is called the context vector. The context vector is essentially a summary of all the input words, but it focuses more on the words with higher attention weights. The context vector is then combined with LSTM's current, so it basically uses the attention weights and then converted into a vector called as context vector. And this context vector is then combined with the LSTM current hidden state to generate the file. Okay, so then it is passed to the LSTM current hidden layer, and then it generates the output based on the based on these context vector, which is actually the normalized scores or called as attention weights. Higher the attention weight, the more the important the word is. The more the important the word is. Oh my god. Yeah, the more important the word is. So yes, let's read it through. I'll still come back to more I guess sections, and I'll still come back and ask for some good examples from for these three, as in how the output looks like. I'm really curious to know. So let me read the analogy, and if not, I'll come back. So the simple analogy will be attention in a conversion. Imagine you are translating a long paragraph from English to French. Each time you translate a sentence, you might want to look back at specific words or phrases in the original paragraph. You don't try to keep everything in your head at once. You selectively look back at the find and to find the parts that are most relevant while you are currently translating. Okay, so the analogy is that we are translating a long paragraph from English to French. We don't remember everything to punctuations, connectors, and everything. We just take out the context and then convert it into French. That's what exactly LSTM is doing. These things are doing. It takes out the important words by assigning score to them and then uses them to generate the output. See, the attention mechanism in the LSTM works similarly. It looks back at the input sequence and decide which parts are important for generating each word of the output. Correct. So the analogy makes sense. Now let's read a little more. It says attention in machine translation. In machine translation with LSTM and attention, the encoder reads the entire input sentence and produces a sequence of hidden states. The translation with LSTM and attention. Let's read it a little more. The encoder reads the entire input sentence and produces a sequence of hidden states. At each step of the decoder, the which generates the translated sentence is called decoder. The attention mechanism helps decide which part of the input sentences are more relevant to the current word being generated. Okay, it using the attention mechanism that we have read just now, the three steps, it decides which parts of the input sentences are important, most relevant to the current word being generated. Correct. This means that the model does not just rely on a single hidden state at the end of the input sentence. It uses information from all the hidden state and focusing more on the most important one. So it has the, the the summary of this thing is that it has multiple hidden states and uses the context vector from all those hidden states to decide to focus more on the important ones. Type, then we have some types of all attentions. There are a few common type of attention used in machine translation. First is global attention and second is local attention. uh, The global attention model looks at all the input words when generating each output word, and the local looks at a small subset of the input word, which makes it more efficient and sometimes more accurate for the longer sequence. Okay. The global looks at all the words at once. The local looks at a small chunk of the word or subset of the input words and then generate them, and then look at the small subset of the word and then generate it. This is more efficient as in it generates better output. This is what ChatGPT says. So it makes sense. I do understand how it works, but I'm still curious to know the how the exact output looks like for scoring the input, generating the weights, and how the context vector looks like. So this is I understand. This is I understand. Um, but just wait. I do understand it, but I am curious to know how does this how does the scores are calculated, and also how is this context vector look like? How does this context vector looks like? Can you give some examples? Let me ask. My god, it has updated. I need to ask it to just explain it to me, don't? Okay, so it has generated the output. So it says, thank God it has not generated. Okay, failed at to edit attention theory LSTM. Okay, thank God it has not added that. It was looking a little weird. So it says, so scoring, to understand how scores are calculated in the attention mechanism. The score of each input word indicates how relevant that word is to the current output word and the model is generating. The score is often calculated by using a simple layer in the network, like taking the dot product between the current input state of the LSTM and embedding of each word in the. Okay, so it produces a dot product of the current state of hidden state between the current hidden state of the LSTM and the embedding. So if you remember, yesterday we did embedding before we passed the. We had an embedding layer before we had LSTM layer while we were training the model. So yes, so we do a dot product of the current hidden state and the embedding of each word, and the dot product essentially measures similarity. The higher the dot product, the more similar the two vectors are. Okay. For example, imagine we have input sentence of four words. I am learning LSTMs. Let's say our LSTM is trying to generate the next word in the translated output. Okay. Let's say our LSTM is trying to generate the next word in the translated output. The LSTM's current hidden state is compared with the representation of each of the input words to get score like 2.0. So these are all the words. They all have some embedded meaning. So now, in order to predict the next word, what it is going to do, it is going to perform a dot operation of this. Just a second. Sorry, I got a call. So yes, where were we? We were exploring this example. So it says we have these words and we do embed them, we do convert them into a numerical form, and then we perform the dot operation. So this is how the score looks like. Okay, so score for each word looks like this. I has 2.0, 0.5 M, learning has 3.0, LSTM word has a score of 1.5. This means that the word has the highest learning has the highest score of 3.0, indicating it is most relevant at this point. Correct. Now generating weights is basically normalizing them using softmax. So after normalizing, this is how they would look between the range of 0 to 1. And then context vector would look like each input word is represented by a vector of numbers called an embedding. Yes, we saw and learned it how it is being calculated yesterday only. So embedding converts each input or each word into a vector. So this is the vector for I, this is the vector for M, this is the vector for learning, this is the vector for LSTM. And the context vector is calculated by taking weighted sum of these embeddings based on their attention weight. So context vector is calculated like this. So the score of this I was, from this we can see the score of the word I was 2.2, and after generalization it was 0.25, the second step. So it multiplies 0.25, a dot operation on the vector, and this is how we get the context vector for I am learning and LSTM. This is how it looks like. Now add all the vectors embedding together. Now we add all of these together, this, and this is the result. So this is the context vector of the input sentence like this, and it serves as the summary of the input sentences with a focus on the important words. So which are the important words here? We can see this is an important word, this is somewhat similar. So we did see that this is an important word. Earlier we saw that this was an important word. What did we see? What did we see? Yeah, this was important, and this had the highest score, and here also after normalization this has the highest number. But after doing the context vector, which is having a dot product of the score and the vector representation of the number, we got to know that this was the, and after adding up all together, we got the final vector that looks like this. This has the highest value. It will be used now. This summary of the input sentences with a focus on the important words will be used along with the LSTM's current hidden state to generate the next word in the translated sentence. Correct. So this will be used to generate the next word along with the current hidden state. So yes, we do understand how it looks like. Coming back to the things, we understand. We also saw how the output, how the conversion looks like this in the form of numbers or with an example also. We also saw that there are two types of attentions: global attention and local attention. The global attention converts all the words, input words all together. Local looks at a small subset of input words, which makes it more efficient and sometimes more accurate for longer sequences. So our attention makes LSTM much better at handling long sentences and complex relationships in sequences by selectively remembering important information. Correct. So it was a good day. Tomorrow we'll go and code it up what we have explored today. So yes, stay tuned. Come back tomorrow and uh, yes, we'll code it up together. Thank you.